what you want to do, but if it happens to be what you want to do, then maybe you do this. All right, so, well, not that, because those are all my programs. So second plus, you go into memory management and delete. All right. It's aggravating because you would think clear entries would be the one that does it, but that'll not be the one that does it. All right, and then you see that there's an option, matrix, and then what you do is you just identify the one that you want to delete by just hitting delete on it. All right, so you will have wiped out all the entries within those matrices, and then once you go back in, you can see that there are no corresponding values associated with matrix A, B, C, or whatever. So again, that is second plus option 2. You go to matrix, and if you have any matrices there listed, that's because you have stuff stored into them, just by hitting delete on them. Not clear, because you're in memory management and delete. All right, so like delete is pretty dangerous when it comes to these calculators, because usually when you select delete something, it deletes it. But this is one of those situations where it won't delete it permanently. It'll just delete the entries within it. All right, while you're in there, you might see that you come across one that says list, and you could see that there are certain amounts of storage associated with the different lists that I have. So stat edit, because I have information stored in my lists. All right, that's not a whole heck of a lot of information, so it's not like it's weighing down the calculator. But if I wanted to, I could wipe out those lists one at a time, but I could also just select clear all lists. It'll say done, and when I go into my stat editor, it'll wipe them all out that way. All right, so if you want to do it one shot, that would be the way to go. The other way, second plus option 2, I don't know that I would want to do that for lists, only because if I'm going to delete them one at a time, why not just go into the list? Or clear them one at a time, why not just go into the list function? All right, so that's that, just a little something, public service kind of thing. We will actually be working with a little bit of statistics before too long, so the stat editor is something that we will have a little bit of experience with. All right, so if you're familiar with the terms term linear regression and the term correlation, those are going to come up, and we're going to see how to derive those formulas using matrices. All right, so pretty cool stuff. And then we'll also get into some calculus. Oh, sorry, page 87. 87, yeah. Steady state vector for P. I can use my my app here for this, because I took the time to put the program in. We're getting close. I'm starting to learn how to use the Apple Classroom. Once I have that down, then and everybody has tablets, then nobody will need graphing calculators anymore. They could use this app, and then I can just lock your iPads so that you could only use the apps I want you to use during tests. And those apps would be GeoGebra, some sort of writing app, and a graphing calculator app. And it'll be great. Forget paper, we don't need it anymore. We just need an abundance of electricity. So, much easier. Anyway, so what we're gonna do is we're gonna come up with what we defined as an initial state vector. Now the issue here is, well, it's not really an issue, I guess, but you might be concerned and thinking to yourself, well, normally we're given that piece of information. So, well, what do we do here? All right, so what we're gonna do is we're gonna create an initial state vector. All right, this situation doesn't have any context, so really you can make up whatever vector you want, it doesn't matter. As long as that vector is a probability vector that adds to 1. All right, so for example, I'm going to keep it simple, 0.5, 0.5. In the absence of information, I'm going to say all things are equal. All right. vector. All right, that's all we're doing here. So you can do that right in the calculator. You don't even have to write the operation. But if you want to, you define this as vector v and say PV equals, and then go from there. But ultimately, we're looking for a steady state vector. So really, it's not what it equals, it's what it's approaching. So it's going to be approaching some steady state vector. So I would put in, yeah, wrong menu. Oh, I was like, where'd my, I thought I deleted all this. I deleted it on the other calculator. Not names. Got my wires crossed. So I need a 2 by 2. 0.6, 0.3, 0.4, 0.7. Double check a Ruski there. Pop in my second my vector, second matrix, vector matrix form, 0.5, 0.5. Now you could start off anywhere you want. And then program, mark off. Well, it moved off of its original vector. It's continuing to move off of its original vector, seemingly approaching something. It's possible it's not approaching anything and it's divergent. If that's the case, then this is one terrible question, because I'll tell you on a test, I'm not going to ask you to find a steady state vector if something is not ever going to converge onto a particular value. Now, if your matrix is a probability matrix and you're dealing with a probability vector and they satisfy the requirements of Markov, then you're not going to have a problem. All right. So I think I've long passed when we would have had a satisfied equality, and we know that my calculator is a little bit different from yours in that it doesn't settle on a decimal value quite as nicely, as quickly. But it's at this moment that I have no difference between my two vectors. All right. Yours probably gave you a nice fractional value, maybe. I don't know. Maybe it didn't, but after 22 iterations, we're gonna get, it's an approximate for me anyway. If you get a clean one, you get a clean one. That's great. 0.429, which is what I probably could have gotten after like the first 4 iterations, but still. 0.571. All right, rounding is okay as long as your 2 rounded entries add to 1. All right, because it still has to be a probability vector. So the entries within that vector have to add to equal 1. So whatever you round it to is fine appropriately as long as those 2 numbers still, or 3 numbers if it's a 3-unit vector, as long as they add to equal 1. All right, it has to satisfy the rules of probability also. You might come up with a different number of iterations. When I make the answer key for the test, I make it off of the graph, not this app, the graphic calculator, so it'll be consistent. But generally what I do is I take your initial state vector, put it in my calculator, and just keep hitting enter until I get the steady state vector. If the number of iterations you came up with is the same as the number of iterations I come up with, then full credit. All right. So that's how you get the full credit for this, because remember, the alternative is to do all this crap by hand, all right, which we absolutely, positively do not want to do. All right, so you come up with a steady state vector, which is a product, repeated products of P and V, and it also indicate what the number of iterations were that got you to that. All right, so really, not too many ways to screw this up. Yeah, that's what I'm saying. Because on this app, it's a little bit different. So when I'm grading it on the test, I'm going to be using a regular graphing calculator, so it'll match up perfectly. All right. So, yeah, slight differences when I use the app, but that's okay.
I think I might have missed this. Is there a reason why you chose 0.5, 0.5?
I just needed to come up with some initial state vector. Didn't matter what it was, as long as it added to 1.
Oh,
So
okay.
I needed 2 entries that added to 1. As long as they followed the rules of probability, I was going to be okay. If you did 0.7, 0.3, that would have been okay also. Right? Anything between 0 and 1. It's kind of like, oh geez, it's really hit or miss as to whether or not people ever learn this. And that's the one drawback about this environment. Well, okay, so who am I kidding? There's like 1,300 drawbacks about this environment, but there's also like 1,300 different positive attributes of this environment too. So I don't want to badmouth anything, but one of the drawbacks is that I could have a class of 30 people, and every one of the 30 people could have had a different Calc 1 teacher. I mean, it is entirely possible that that's how it played out. And so I really don't know what you got in Calc 1, right? But what you should have got was a concept called Newton's method, right? It's a method by which you could find solutions, zeros to a function, using differential calculus, right? It's an iterative process, very much along the lines of what we're doing here, just using calculus techniques, right? And so the idea is that you're finding the ratio of a derivative to its function, and then taking that result and plugging it back into a formula, getting a result, plugging it back into the formula until you settle onto the correct answer. The closer you are in your initial guess to the correct answer, the fewer iterations it takes you to get to the final answer. All right? So if Newton's method is something that you've experienced and you know exactly what I'm talking about, if not, then experiencing this might help you understand Newton's method, right, if you ever get to that. What I'm saying here is, had I selected 0.4 and 0.6 as my initial state vector, I would have gotten to this solution using fewer iterations. All right, so if you have a sense of where the distribution is going, and you wisely choose an initial state vector that would be more in line with that information, then you could get the solution much quicker. The caveat to that is, well, you're just hitting enter. So, okay, you just had to hit enter 5 times. I had to hit it 22 times. Right? So it cost me an extra 20 seconds of just hitting enter. I wasn't really thinking. Right? So if you had to do it by hand, massive difference in difficulty. Also, we're not given any context whatsoever here. So, like, what am I going to get out of this? You know? So, like, how could I come upon an initial state vector that's more meaningful? It's not even remotely possible. All right, so. Second example. And highlight a couple of things. All right. So it's a probability matrix, like as in probability. So yeah, the columns have to add up to 1. That's all wonderful news. None of them happen to add up to 1, by the way. But the 0. Aside from that, probability values of some event x have to exist between 0 and 1. All right, so this is not an appropriate probability matrix. All right, so this is a trick question. So let's actually just play it out and see what would happen. So I'll go with my initial state vector v equals 0.5, 0.5. Oh, 0.5, it can't be that. It took a second. I'm a little slow tonight for some reason. 0.5, 0.3, 0.2. And it's got to have 3 terms because it's a 3 by 3 matrix. All right. But aside from that, I mean, you might be thinking, well, what does it matter? Like, the probability matrix is all screwed up anyway, so it ain't going to work.
Probability matrix, well, invalid syntax in general, but is focused around 0. Should the initial state vector not also be focused around 0?
Not even, because once it fails for the probability matrix, it's going to fail completely. Now, for some reason, oh, I see what's happening. 3. Why is it kicking me out? Oh, because you know what? I never ended the program. That's why. I was like, it's not letting me edit my matrix. So, what's up, man?
Do the elements of the probability matrix have to be greater than 0?
The elements of the probability matrix. No, you could have a probability equal to 0. Yeah, as long as the columns should be between 0 and 1 inclusive. So, as long as the columns themselves add to equal 1. So you could have.
That is valid.
Sorry?
So that,
My V is good.
right, but then wouldn't the probability matrix be valid if you're saying that the sum of the columns has to be between 0 and 1?
Oh, no, sorry. Each entry has to be between 0 and 1. The sum of the columns have to be equal to 1.
Right.
Yeah. So negative 0.3, 0.1, positive 0.3, 0.2, negative 0.2, and then negative 0.6. All right, so quit out of there. And this is a 3 by 1, 0.5, 0.3, and 0.2. And then I run Markov. So I get an entry. All right. That's not any more appropriate than any other entry. So it's violating every rule. I mean, well, we broke the rules in the probability matrix, so why not continue breaking the rules? Then you see this, and you continue. Yeah, it seems to be zeroing out. I mean, we get some scientific notation in there, but ultimately it's getting smaller and smaller to the point where it seems to be asymptotic in each case towards 0. All right, so what we're getting is a meaningless result because we're getting a probability vector that's saying 0, 0, 0. So if we were to say a steady state, and you know, this is actually, believe it or not, an acceptable answer. The steady state vector in this case would be 0, 0, 0. But I wouldn't even start the process. You know, it's a trick question because there is no meaningful result. But you could also say 0, 0, 0 because all entries are impossible. All right. So there is no probability model that could satisfy this situation. There's no probability vector that can be satisfied by this. All right. The only thing that you can get is the 0 vector, which is trivial. All right. So each entry, all entries are impossible. All right. But again, for a question like this, I wouldn't even start the process. And I have kind of a tug of war with myself on this, where when I put a question like this on a test, I feel like it's kind of unfair to say find a steady state vector knowing that it's not possible. But then if I say find the steady state vector if possible, then I'm basically telling you what the answer is. So you just got to be on guard for stuff like this. All right. And if I guide you to it, I'm giving it away also. If I say determine whether the following refers to a probability matrix and then find, if possible, the steady state vector, then it's like it's all over. It's not even a question anymore. I might as well tell you what the answer is.
In general, to be able to use the Markov's chain, all entries must be between 0 and 1?
Each entry has to be between 0 and 1 inclusive, except, you know, if you have, for example, a 1 as an entry here, then neither of these entries can be anything other than 0, right? Because the columns all have to add to 1 also. Because each vector that makes up your probability matrix must be a probability vector itself, all right?
What if like all the vectors like add up to like something else, like 0.5?
Nope. Does not satisfy the rules of probability. Right? Because what we're really dealing with is a probability distribution for each column, and a probability distribution accounts for all possibilities. If you're dealing with all possibilities, you're dealing with 100%. 100% in decimal form is 1. So if you think of each one of these entries as a percent of the whole, where the total of each column represents the whole, then it should make perfect sense what you're looking for. You're looking for a percent value in decimal form between 0 and 1, where each column has to add to equal 1. And that's the same thing is true for your initial state vector. All right, eigenvalues and eigenvectors. So, really kind of weird. Like, let's go back and forth on whether I should tell students what eigen means, because it's kind of anticlimactic. Because you expect it to be this some origin story, you know, that really like is an eye opener, like something really extremely powerful. So, well, okay, I decided. Eigen just means proper in German. Sounds fancier though. That's all that matters in life, right? You know, book by its cover. That's how we judge things. Yeah. I don't know. I figure, you know, like I'm being tongue in cheek about that, but I gotta figure that to some extent that has to be true. Otherwise, like, how are so many imbeciles like in charge of so many things? Like, somebody goes in for an interview and they're not qualified for a job, but then they get the job somehow. So something in terms of like lack of depth must have taken place there. So, you know, the origin story behind this is really very simple. It's like, yeah, eigen sounds better than proper. We're going to go with eigenvalues. It does sound kind of cool though. So we're going to learn what eigenvalues are and eigenvectors. It's actually pretty straightforward in terms of why they're valuable. Eigenvectors are really just vectors that are unimpacted by the transformation process. Right? So a vector that doesn't move after a transformation. Right? So and transformation, the matrix multiplication, is how we transform vectors. So if I wanted to transform one vector to another form, maybe to another basis, I would multiply it by some other matrix. So, you know, whatever my basis matrix is. All right. So we did that with rotations. You know, just find out, like, the simple way of saying it is, where do you want I and j to go? Where do you want your unit vectors to go through the transformation? Well, that's going to be your transformation matrix. All right. So what if there were some vectors out there that, even though every other vector around them were being transformed into new locations, that one would stay put? All right, that's what we call the eigenvector. All right, a vector that, when operated by a given operator, gives a scalar multiple of itself. That's the same thing, just less interesting, I guess. And so the eigenvalue gives us the strength of the stretch or shrink. I mean, I can't really speak anymore. I might as well just call it a semester. Of a vector after a given operation. So is it going to be a massive elongation, or is it going to be a teensy tiny shrink along that same direction? But ultimately it's still in that same direction. That's what matters. Right? The eigenvalue is any possible scalar that could give you a vector that lies along that path. Right? So basically, if a vector is resistant to the transformation process, then it's going to be considered an eigenvector. And an eigenspace, well, we're just eigen everything now. If we're defining an eigenspace, well, the vector space is the basis of the vectors, the vector system that you're working with. So why would an eigenspace be any different? Right? So it is basically the set of, or the basis of the eigensystem. All right, so if you have a set of eigenvectors, and then you determine what the column space of those eigenvectors are. So you have a matrix that's defined in terms of eigenvectors, and you find the column space, because remember there's column space and there's null space. The column space is defined based on the pivots. Whatever columns have the pivot values in them are defined as the vectors that make up the column space. So if those vectors also happen to be eigenvectors, they make up the eigenspace, right? So everything else is going to be the null space, all right? The process is procedurally very simple. Conceptually very simple. Procedurally very terrible. Nightmarish. Nah, it depends. It's like everything else. It depends on how complicated the vector space is. So, you know, we have to do some algebra, which is kind of surprising because we haven't really had to do much of that. You know, like it's been this course called linear algebra that doesn't have much algebra in it until now. Now we're going to do some algebra, right? So it involves a determinant of what's known as a characteristic polynomial. Right? That characteristic polynomial is the difference between a scalar, that scalar that we're calling the eigenvalue, which I already scrolled past, and the given matrix A. Right? So we're finding the difference between that scalar and the matrix A, and then making the determinant of that equal to 0. And I'll talk about why that matters in a little bit. But that gives us what's known as the characteristic equation of A, and that's how we're going to be able to solve for the particular eigenvalues. All right? And then once we have the eigenvalues, we can determine the eigenvectors. All right? So it's really just this relationship. Now, I can say that this can also be written as the determinant of A minus lambda I. Because once you find the determinant, if you were to swap the order, it wouldn't really make a difference because you'd just be factoring out a scalar of -1 and then dividing 0 by that anyway. So they end up being equivalent to characteristic equations. The only reason I bring that up is because what happens, I don't know, maybe it's just me. Maybe I'm literally the only person on the planet that ever screws this up. When I get started on the process of trying to find eigenvalues and vectors, I'm like, all right, here's my matrix A. Oh, crap. What I wanted to do was write my identity matrix first, then multiply that by lambda, and then subtract from it A. But I didn't do that, and I've already written matrix A. So I can easily adjust matrix A. Going the other way is less convenient. So I'll show you what that means in a minute, because all this is like in a vacuum. So. Solved examples are wonderful. You could read them if you want. I don't know why I do that. Because I just skip over them anyway. Or I talk through them really fast and nobody gets anything out of it anyhow. So, yeah, we're hopping up to page 90. I'll probably save a page on that. You know what I could do? I'll take this as a typo. I could take that page out and put it on my website as a tutorial page or an extra practice page, save myself a paper page, but still have it available to folks. All right, so if anybody wants to submit that for a typo bonus, you're welcome to. You're the best. I have fun with this stuff. All right, so determinant. So it's either lambda I minus A, or, like I said, we could do A minus I lambda, or lambda I. All right, it really doesn't matter which way you go. Now, the dimensions of I should be consistent with the matrix that you're given. So this is a 2 by 2 matrix. So this is going to specifically be lambda I sub 2 minus A. all right? I sub 2 is the 1, 0, 0, 1 matrix, all right? So I'm looking at the determinant of, well, 1, 0, 0, 1 multiplied by lambda. So lambda 0, 0, lambda. Oh, nope, 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 undo. Now that's right, but we have to subtract from that a. And then find its determinant. All right. So we're looking at lambda minus -1, so lambda plus 1. 0 minus 4, so -4. 0 minus 6, -6. Lambda minus 9. That determinant needs to be equal to 0. So each one of these expressions should be parts of equations that are equal to 0. All right. So if we solve this characteristic equation, what we'll have is the set of eigenvalues, if they exist.
So it always has to be 2, 2, or 3, 3, 4, 4.
Yeah, it's got to be. They have to be square matrices. Yeah, you're not going to have an eigenvector that exists in a matrix that's not a square matrix. Good question. All right, so lambda plus 1 times lambda minus 9. We start off with the 2 by 2 because it's easy to find the determinant. Now you could also see how this is not really much of a calculator type question because, I mean, just look at it. All right, so minus diagonal up, so minus 24. Or at least it's seemingly not a calculator type question. You could still use the calculator to do the ordinary algebra stuff. I could solve this equation right now using my calculator. I mean, just x's instead of lambdas. Right? There's nothing wrong with that. In fact, I actively encourage it. Right? Because even though the course has algebra in the title, I don't want to do algebra if I can avoid it. Except when I'm teaching an algebra class, at which point I tell them, oh, I love doing algebra. I can do this all day long. And then I walk out of the algebra class, I'm like, oh, thank God that's over. So, anyway, but I'll do it by hand, and then I'll go back and show you how you can do it on a calculator if you don't already know. So, lambda squared minus 8 lambda, assuming my pen wants to function without turning off arbitrarily, minus 9 minus 24. All right, so lambda squared minus 8 lambda minus 33. (11 and 3). Lambda minus 11, lambda plus 3. And so lambda equals 11, and lambda equals -3. All right, is lambda equals -3 an eigenvalue? Yes. And the answer to why is C below.
Do you know off your head that it's 11 and -3?
Oh, well, I just looked at the factors of 33. The only way I was getting to a 33 was 11 and 3. And I just figured, how am I getting to a -8 from there? Like, if I'm going to get from an 11 and 3 to a -8, the 11 had to be negative with a positive 3. A little algebra 1 trick from back in the day might be helpful.
Yeah, I feel like I skipped it.
It's a good trick. And you know what? I'd use this trick all the time. You know, because sometimes like a 33 resonates with me, right? 35, that's another one. But sometimes you get to like 128 and you have like a bunch of different factors that can go into it. So this is coming from the operation of xy equals -33. So basically I'm looking for two numbers that multiply to equal -33. So xy equals -33, all right? So all I'm doing is solving this equation for y is equal to negative 33 over x. And so I'm popping that into the calculator and just looking at the table of values. And just looking at the ordered pairs to see which pair of values would add to give me a negative 8. All right, so nope, nope, there it is. And so now I have my two factors. Okay, it's a little nifty algebra 1 trick that really goes a long way. There's another more complicated way of doing it that involves a stat editor. I don't know if it's necessarily worth it though.
Wait there, I confused.
Say it again, sorry.
I get confused what you do.
Like how I did it? Yeah, so I typed in negative 33 over x. Then I'm going into the table, so second graph. Let me just get into the right neighborhood. I don't know why it knocked me off of my... And then I just start scrolling down the list to identify any pair of values that would add to give me the negative 8 that I'm looking for in the middle. All right. Now, I always forget what the prereqs are for certain courses, but I know you definitely had to take at least some level of calculus to get here. So there are other different, other strategies that you could use. One of them actually might be Newton's method. Honestly, I can't remember what programs I dumped into your calculators. Was it just the two? I gave you Pascal. Did I give you Pascal? Okay. So there was a program that I wrote called Newton's method that could be helpful also. But sometimes just having a simple quadratic formula program in your calculator can be useful. The problem with that is it only works for quadratics. So if we have something that involves solving a polynomial that's not degree 2, you'd be out of luck. So let me show you a technique that's already built into your calculator that's going to work regardless of the technique. So, regardless of the function. So you type in the original equation. So, and this is before any algebra. All right, so I'm not even going to distribute. I'm not going to take the chance that I'm going to screw this up. So I'm going to type in x plus 1 in parentheses. So don't go looking for a lambda key. X minus 9 minus 24. I don't know why that keeps happening. You know what? I'm still in that program. It's like Nightmare on Elm Street. I'm still in the dream, or Inception for a more recent example. I mean, that's pretty disheartening. The fact that the guy never got out of the dream. Brutal. I'm just worried that it's going to happen again. I wonder if I should shut the app down. I'll just roll the dice. All right. So you put your function in, and then as a second equation, you put in y equals 0. All right? Because basically we're undoing the substitution technique for solving an equation. All right? So I'm just basically saying I have an equation y equals this and y equals 0. I want to find where they intersect. All right? There's two ways to do that. One is graphically. So I could take a look at the graph and see if there's an obvious intersection, and then use the functions that are built into the calculator to find that obvious intersection if it exists. All right? So now these are clean values, so I expect that if I just do a regular zoom on my calculator, it should be pretty obvious where those intersections are. All right, so we're looking for x-intercepts, and since they actually happen to be whole numbers, well, one's a whole number, one's an integer, you could actually just count tick marks on the screen and see where they are. But let's say you can't, let's say it's not obvious, or in the case of some of your calculators, yeah, the tick marks are not very trustworthy. Yeah, it looks like it's -3, but I'm not going to bet my life on it. So what we do is we hit second trace, and that brings us to the calculate menu, which I'm going to have to do on the other calculator. Right, so it's too different on this one. And there's no way for me to record this thing. So, well, then I could show you another technique also after this. So that's a little something for everybody in a minute. Let me just put this over here, line it up, narrate everything I do, because, you know, that's not weird. All right, so again, type it in the original function, x plus 1, x minus 9, and then minus the 24, and then the 0. All right, so I'll just do a zoom 6. Now, in this case, all I was looking to do is test to see if -3 was an eigenvalue. So I'm not even looking to see if the 11's on the screen. But if I wanted to adjust my window, I could. I just make my x max something bigger than, well, I'm kind of cheating. I know what the answer is, so let me make it 15. But it's parabolic, so I know I have to have at most 2x intercepts, so that's what I'm on the lookout for. All right, so what we do is second trace intersect, option 5. Then it asks me for the first curve, but what I want to do, and instead of answering their question, I'm going to ask them a different question. I'm going to do something different. I'm going to get over to where the intersection that I want to find is, because I'm finding the intersection between y equals this and y equals 0, which is the x-axis. All right, so if I get to this point, then look at the top of the screen, it says the y equals x plus 1, x minus 9, minus 24. That's my first function. Hit enter. Y equals 0 is my second function. Hit enter. So I clearly identify which functions I wanted to find the intersection of. And then my guess, which is very mathematical. But then again, that's kind of like what we were doing with the Markov chains. I took an initial guess, and then the iterative process carried me towards a solution. This actually is that thing I was talking about before called Newton's method. It's built into the calculator. So I hit enter, and it gives me my solution, the intersection between the 2 points, all right, or the 2 curves. So that's a technique that you could use to solve your equations, but maybe you don't want to do that because you're not confident that you can come up with a graph that would clearly show the intersection between the curves. Yeah, like if you have some crazy polynomial function, or when we talk about partials, some trig function, and you're like, I don't even know what this looks like. How am I going to come up with a window? Another technique that you could use, it's different depending on the calculator you have. Fortunately, I have many. You could use the solver function. So in the math menu, right in the bottom, there's an option called solver. All right. Some of your calculators say numeric solver. All right. So if yours says numeric solver, or if you have a color screen, then just sit tight. I'll show you in a minute on another calculator. But yeah, select that, and some of your calculators will bring up this display. So you might wonder, do I have to do this? And I would say, keep an open mind, because the number of times that I've gone through this process and afterwards a hand goes up, yeah, so you know all that stuff you've been saying for the last 5-10 minutes? Can you repeat all of it? Because I didn't catch it the first time. And I was like, I know what happened. You didn't think you wanted to learn it. You didn't think it'd be useful. And now you realize it's a good way to do it. You want me to teach it again. And then when I call people out, we get a good laugh at it. But I think enough of you will like this approach that it's going to be worth it. So alpha trace y1 minus alpha trace y2. All right, this is what you're going to put in and leave in. All right, this is a function solver. All right, what it does is it takes the difference between those two functions and sets it equal to 0. So if you think about what we put in y1 and what we put in y2, that ultimately ends up being the left-hand side of the equation. All right, the reason why we want to do it like this is so that we allow ourselves to find the solution of any equation, even if the right-hand side is not equal to 0. All right. When you hit enter, it brings you to this. Now, it seems like it just told us the answer. It did not just tell us the answer. All right. Every time I go into this window from here on out, no matter what I put in for y1 and y2, it's always going to tell me that the answer is -3 unless I do something different. All right. X is X. All right. What I mean by that is when we found the intersection, the calculator solved for X. It stored that value in as X. So if I went into the home screen and hit the X key, the -3 would come up. 2 weeks from now, if I hit the X key, the -3 is going to come up. All right. So it just thinks X is equal to -3. All right. So we get that out of there and just put in some default value. For a quadratic, we expect there to be 2 solutions. Whatever number you put in there, the calculator interprets that as your initial guess. And what it'll do is it'll drag your solution, or actually it really is dragging you. It's dragging you to the solution closest to that number. All right, so there are 2 solutions. We know what they are, -3 and 11. By putting in a -10 and then hitting alpha enter, it's going to drag me to the solution that's closest to -10 out of those 2 possibilities. So alpha enter, it just dragged me to the -3. If there was a third solution, let's say a third solution was -12, it would have dragged me to the -12, all right? I got to know to be on the lookout for a quadratic for more than one solution. So what I would do is I put in something around -10, so let me put something around +10 and do the same thing, alpha enter. It drags me to the solution closest to that. If you know that you're dealing with 2 functions that are only going to intersect once, doesn't matter what you put in, there's only one solution. It's going to drag you to the same solution no matter where you start. All right. So it's a pretty nifty technique because even if I put in, I have no idea what the answer is, -100. It might think a little longer, but it's still going to drag you to the nearest solution to -100. It can't get to the 11 without passing by the -3 first. All right, so it will always drag you to the nearest solution to that point. All right, this works for trig functions, works for log functions, pretty much anything you can think of. The only time it struggles is when there's discontinuities. So as long as you're mindful of those things, you're generally going to be okay. But the good news is it's not going to drag you to a solution that is at a discontinuity. So if you had something like a tangent function, when cosine's equal to 0, tangent doesn't exist. So it's not going to bring you to a place like if you're trying to solve tangent of theta equals 0, it's not going to bring you to like pi/2. All right, it'll never take you there. All right, because it knows not to do that. All right, so let me just show you very quickly on the other calculator. Almost everything is the same after you get your initial setup. Let me just get out of the glare here. All right, so math, numeric solver instead of solver. That part you probably figured out. Interface is a little bit different. So if your display looks like this, you actually have the better version because they created a little menu here for you to kind of have a little easier access. I mean, it basically is just going to take what you put in these fields and interpret it the same way we did in the other calculator. It's asking you for your first and second equations, right? For us, that means whatever is on the left and whatever is on the right. Alpha trace y1, alpha trace y2, set it and forget it. Those are things that you should never have to change. I have 37.5 in here from the last time I did a problem like this. All right, cool. Alpha, enter. It dragged me to the solution nearest to that number. All right, but you can see at this point it's the same process. -212 is what I'm putting in. I have no idea what the answer is, so I'm taking a shot in the dark. -3 is the one that's closest to that. More powerful memory, so it goes a little bit quicker, but it's still the same thing. Now you can see here it says bound. This is the calculator trying to say -infinity to infinity. Right? So it's basically an unrestricted domain, but you can restrict that domain if you want. If you only care about positive values, let's say you're trying to solve for solve a probability question. All right, well, you know your answer is supposed to be between 0 and 1. So make your bound, instead of -1e99 and +1e99, make it 0 and 1. So that the calculator knows to only look in that interval. And then make your guess a number in between those two values. All right, it'll drag you to the solution. So it's a nice way to get around being bogged down by the algebra. All right, it's pretty nifty. And also, I mean, I don't want it. Well, I didn't come in here with the intention of getting completely sidetracked by this, but now I'm at the point where it's like, now I'm just showing off. Let's say you're taking like an accounting class and you couldn't remember your compound interest formulas. Actually, I'll tell you, any formula that's explicitly defined, so where you plug in numbers and you expect to get a solution that is also a number, you can use this solver technique to find the solution for you. So let's say you have, I'll do simple interest. What is it, I equals PRT, I think. All right. What you can do is actually put these values in. With the old school calculator, what you'd want to do is subtract the I from both sides, because you need it to be set equal to 0. All right. So 0 equals PRT minus I. And so what you can do is in your your Y1, type in PRT minus I. All right, so that's Y1 minus Y2. That's the same thing as what I would have if I were doing a regular function-based equation. Now when I go into the solver, it gives me not only fields for a field for x, it gives me fields for every one of them. All right, so just think about any equation. Think of a science class where you have a formula where you have to plug in multiple values. Like you plug in 4 values and you're solving for the 5th one. You know, there's 5 places where you could plug in a number. You know 4 of them, and you got to figure out the 5th one. You don't need to do algebra anymore. So you know the principle. You know the interest rate. But I thought, whatever. You plug in the numbers and then you solve for the missing one. So I'll just make up some things like 100.025, and then alpha enter on the one that you're looking for. All right. So it'll automatically solve it algebraically for you. So this is the closest the calculator gets to symbolic manipulation. All right. But very, very user friendly, provided you know how to use it, you know, and you're friendly. Okay, so anyway, the next one, we start to jazz it up a little bit. Is 1 an eigenvalue of this? And if so, find the corresponding eigenvector. All right, cool. We're just gonna find the eigenvalues and eigenvectors. Because these examples, the way they're phrased, they kind of assume that the previous page happened, you know, as in, like, you tried all those problems, we went over them together, but they were all typed, so we didn't. And so I'm using these problems as a way to introduce the concept. All right, so I need the determinant of the appropriate identity matrix multiplied by the scalar lambda, that minus this A. All right, this is what we're calling, again, A. So lambda I is going to be lambda 0, 0, 0, lambda 0, 0, 0, lambda. We're subtracting from that A. We don't really want to write the entire matrix again. Then we're finding the determinant of that, setting it equal to 0, and we're coming up with what, again, we call the characteristic equation. All right. So we're looking at lambda minus 4, 0 minus negative 2, so 2, 0 minus 3, so negative 3. So basically, lambda minus whatever's going down the main diagonal, and then reverse the signs of everything else. All right, so 0, lambda plus 1, negative 3, 1, negative 2, lambda plus 2. All right, so this is what we have to find the determinant of. And oh dear Lord, are we in for it. Because if we're going to find the determinant of this, we're either going to, well, we're going to do one of two things. We're going to put this in triangular form, diagonalize it. We can't do that yet because we haven't learned it. So triangular form, because if it's in triangular form, you just multiply down the main diagonal and call it a day, and that's your determinant. Or we're going to use cofactor expansion. All right. So the idea though is we want to pick a nice convenient row to work with, and so it appears in this case that the nice convenient row does not exist, but we'll settle for row 2. All right. So zero multiplied by, I probably shouldn't even write it there. I'll do it up here. Now, this is entry 2, 1, right? So negative 1 raised to an odd power is going to be negative, all right? So 0, though, it doesn't matter, but that's telling me that my alternating signs is going to be negative, positive, and so on, all right? So if we were in the first row, it would be positive, negative, so we got to be mindful of that, all right? So my second term or coefficient would be lambda plus 1. And then negative 3, but it's minus a negative 3, so plus 3, as it turns out. Smidge it over here. And so now I just need my ingredients. All right, so if I wipe out the row and column that 0's in, I get a matrix, but I don't care about that matrix because it's going to multiply by 0 anyway. So I'll just put a big old X in that. All right. If I wipe out the row and column that lambda plus 1 is in, then I'm looking at lambda minus 4, a negative 3, a 1, and a lambda plus 2. All right, if I wipe out the row and column that negative 3 is in, then I'm looking at lambda minus 4, 2, one, and negative 2. All right, so yeah, at least we got rid of one matrix. But hey, ultimately, it's really not that crazy in terms of the act of finding the determinants. It's just solving the characteristic equation. That's where you start to earn your keep. Now, imagine if you had to do it algebraically. Now we'll see. Maybe it's a bad example. Maybe it's very easy to do it algebraically, and I'm just making up stuff as I go. So lambda minus 4 times lambda plus 2, then minus a negative 3, so plus 3. Then I'm going to have plus another 3, but this time multiplied by I'm going to do 2. Nope. Yep. Plus 3 times, I'll write the negative 2 in front, lambda minus 4 minus 2. And that whole shabiggity bangity boom here should be equal to 0. All right. So you can go ahead and distribute all this out, or this one has too much glare. I just can't do it. This one, at least, the glare doesn't impact things too much. All right. So, again, my whole thought on this is, if I'm going to let the calculator do it, I'm going to let the calculator do it. I don't want to do any work. That's just a general rule of thumb. It just so happens life and linear algebra are coinciding tonight. So I'm just typing this in. Just everywhere I have the square brackets, I'm using parentheses, but still, it's the same. Same but different. I am blowing up here. It's just mostly typos. It's like everybody from all of my classes are deciding to submit all of their typos right about now. What can you do? So I could look at the graph on this, but you look at what we see here, and it's like, maybe not. Maybe the solver is the way to go. So math, solver. Now, they told me a solution here. I just can't remember. Was it 1? Yeah, 1. All right, so I'm not really on the lookout for a 1, but I'll try it. You know, I'll put in something close to 1. All right, so it verified the 1, which is great, because my big concern is that I did something incorrect leading into this step. All right, but the fact that 1 came up as a solution is pretty solid. But we do have some quadratic components in here, and we have an additional component right here that could lead me to believe that maybe this is even a cubic. All right, so now I want to see if there are even more solutions. So let me try something like, well, I put in a 2. Let me try something negative. All right, that's a lovely looking answer. All right, so I don't know what that's equivalent to. If it's a clean number, maybe it'll math frac. But the thing is, you should not really be expecting this to math frac, all right? Because what happens is the calculator is really working with an approximation technique to come up with these solutions. That's why the 1 came up as 0.999 repeated. So it's good enough to give you an idea of what the correct answer is going to be. Sometimes it'll tell you 2.0000001, so you know that the calculator is trying to say 2, but that doesn't mean it's going to math frac to something meaningful. All right, but we have a solution of about negative 3.61. All right. So we know lambda. We knew lambda going in was equal to 1. Approximately negative 3.61. Now let's see if there's another one. Solver, let me put in something large, like 20. Oops. And alpha enter. I got the same thing but positive. All right. If that one didn't math frac, there's no reason to think that this one would. It's the exact same thing. Sometimes it's subtly different at the end that you never know, but we could just pop the plus or minus on there at this one. Say it again? Square root of 13 is clean? Well, it is quadratic, so it makes sense to, oh, of course it is. The one thing I didn't check. So 1 plus or minus root 13. Yeah, so if something doesn't math frac, sometimes, most of the time anyway, it's because it's irrational, but sometimes it's because it's the square root of a number. So take that decimal, square it, and see what it is the square root of. Turns out in this case it's the square root of the prime number 13. So that's good. All right, so we have clean-ish values. All right, so now what we have to do in order to find the eigenvectors is solve the homogeneous equation associated with these eigenvalues. All right, so we're going to go back in time real quick, and I'll show you the relevant. Yeah. Why did that not lock in? Well, I must have missed something here.
I think it turned on.
Yeah, but I can't even do anything with it now. And that's just going to aggravate me to see that there, like in my face the whole time. Right, okay. Oh, okay. So now I can just move it out of the way. Just chuck it up there. All right. So now what we're doing is we're taking this matrix and redefining it if, for example, lambda is equal to 1. My lambdas tend to look like x's from time to time, so you know I'm intending for them to be lambdas, but if at any point you're not sure, just say something because it's kind of a big deal. All right. So we're looking at if lambda is equal to 1, we have -3, 2, -3, 0, 2, -3, 1, -2, +3. All right. We're solving the homogeneous equation, and we know that that just essentially means that we're just giving a column of zeros.
Is that one x? Can you get x equal to 1?
Oh, that's just me being stupid. That's supposed to be a lambda. That one I have no excuse for whatsoever. Thank you. So, the trade-off, you know, like we get to do more, cover more, but you still have to type all this crap in. It's just, it is what it is. All right, so we're going to RF this bad boy. Good old RF, always coming back. An old friend. All right, math bracket. Ever so slightly changed. So 1, 0, 0, 0, 0, 1, -3/2, 0, and then 0, 0, 0, and one final 0. All right. So we're looking for the solution, and because it's very easy to lose sight of what we're doing here. This is the solution of the characteristic matrix multiplied by x. So this is lambda I minus a times x, this time it really is an x, equals 0. Poor quality lambda, so let me just fix that right quick. So lambda I minus a times x equals 0. So what we get as a result here is x equals. All right. So this amounts to x1 equals 0. x2 is equal to 3/2 x3. x3 is our free x3. So x3 is equal to x3. And so what we're going to get as a final result here for this particular eigenvalue, we will get the corresponding eigenvector x equals x sub 3 multiplied by 0, 3/2, 1. All right, so this is the eigenvalue, eigenvector with eigenvalue of 1. All right. But the issue is we have 2 more eigenvalues. All right, but it's not really that much of an issue because it's all calculator work. It's just we have to put in those eigenvalues in for A, matrix A, well, quote unquote A, it's really lambda I minus A, but we're replacing each of these with a radical 13 first and then a negative radical 13. But it's still the same stuff. It's just our answers aren't going to be quite as nice because we're dealing with a radical, but we can live with it. All right, so I'm going to steal the space for the next question. Well, I'm going to put a star on the next question because we're getting close. By the time we're done with this problem, we should be pretty much there. All right, so if we have lambda is equal to root 13, everything else in the matrix is going to be essentially the same except for the values along the main diagonal. All right, so it's going to be rad 13 minus 4. Then 2, negative 3. Then 0. Then rad 13 plus 1. Negative 3. Then 1, negative 2, and rad 13 plus 2. All right, so all I'm doing is replacing each one of these values along the main diagonal. I'm replacing the lambdas with a rad 13. All right, and then when we get around to it, we'll do the same thing with lambda is equal to negative rad 13. All right, so it's all going to be the same stuff, just with negatives. So negate main diagonal. Well, negate the negative 13. I don't even have to write that now that I think about it. I'll just snip what I put in the calculator. But go into my matrix editor, and I'm only just changing 3 values. So I'm drastically changing them, sure, but it's only 3 values. So radical 13 minus 4 converts it automatically to decimal form. All right, radical 13 plus 1. Same deal, automatically to decimal form. Radical 13 plus 2. All right, there's no reasonable expectation of a math frac here when we do the RF, so we're just going to go with the decimal values. But a little copy paste. I mean, you could try to math frac it, but again, no reasonable expectation. No change whatsoever. All right, so I'll just do a quick snipperooski here. I'll edit it, but then I'm not going to paste it in because then what I'm going to do is simultaneously handle the other one. Oh, it's done. I just want to save the photos. All right. So then back into the matrix editor. So this entry is going to be this negative square root of 13. Minus 4. Negative square root of 13. Plus 1. And then negative square root of 13 plus 2. All right, so we run those numbers again, but this time I'll actually snip this matrix and put it in there because I didn't write it out. All right, so RF that, and we get this bad boy. All right, so picture existing. So that's that one. Cockeyed, but it's all right. All right. Still a little, whatever. All right, so now we just want to state the eigenvectors that are coming from this. So this is, again, the matrix equation. Both sets of matrix equations associated with the eigenvalues, specifically of rad 13 and negative rad 13. And so this is the R ref variation, both of them. All right, so pretty ugly, but we can get a pretty easy way of representing these, because as it turns out, in each case the free variable is the third entry, which would be in each case x3, and all we're really doing is negating the third entry, which is corresponding to x3, so we're in good shape. So x as a solution for the second eigenvalue should be equal, and we're going to approximate x3 negative 4.30, I'll say 303, positive 0.651, and 1. All right, because again, that free variable of x3. All right, so it would be the same as if I wrote it out just like I did right here. The free variable gets the coefficient of 1. So x3 equals x3. So that's the same thing that happened here. And these other ones, they just, well, this one was a 0. This one just got negated. All right, so that's all I'm doing here. So I'll do the same thing down there. And we can kind of, sort of cut to the chase a little bit. All right, so these are the three eigenvectors. Because what happens is, when I show the intermediate step of writing it as x equals 0, x1 equals 0, x2 equals x2 equals 3/2 x3, it comes from adding this term to the other side of the equation. And so here I have a positive value that I would be adding to the other side. Subtracting from the other side, and a negative that I would be adding to the other side. All right, so it's just the operation that's changing the sign. All right, so depending on what we're using this for, there's a variety of different ways you can represent your eigenspace. Even though they're not asking us specifically in this question, there's a lot of things that weren't asking us for. So the reality is, if you really think about it, based on what the question was asking us, this, and this was all I needed to do. All of this other stuff was for me to teach you things, all right? Because you're going to need to know it anyway, so I figured no time like the present, all right? So the basis of your eigenspace would be these three vectors. Doesn't matter what order. When we learn next class about how to diagonalize a matrix, and then all the wonderful things that happen, well, not really happen, but all the wonderful uses of that concept, then you'll see that the order in which you represent your vectors will be important. But for now, not so much. All right.
Question. So if we're extending that logic and saying that the basis of the eigenspace is the space formed by all the eigenvectors for the problem.
Then the next question is flawed. Yeah, I just saw that too. Whoop.
Well, what's actually funny is that you get a repeating 3 when you solve the polynomial.
Oh, I don't even remember that.
I have no idea to do with it, but you get a repeating 3.
Well, it's just going to correspond to the same eigenvector, so it's fine. Right.
It technically does mean that the space then would be only the basis of that space would just be then the singular vector.
But there should be, because it's 3-dimensional, there should be, if you have, is it repeating 3 times? So 2 times, so there should be a third one. I'm sorry, a second one that is unique.
Would it be the 0 vector?
Well, if it is, then that's a problem, but.
I mean, I don't know what else it could be if you go through.
Right, I mean, it could be an eigenspace, but it wouldn't, it would have to be a subspace of the real space. So it couldn't form the basis of real space. It would have to form the basis of a subspace rather than the entirety of the whole. Which is fine. It's just not quite what I had in mind when I created the problem. So, but we'll tackle that one.